Okay, so now last time we discussed one single loop circuits, and we're going to be making use of the loop law quite a bit today. So we really want to review it to see what happens. So in order to look at the loop law, we're just going to pick a point on a circuit, right, A, and we're going to pick a direction for the current. And we have this direction of the current going all the way around the circuit. You'll already notice it's labeled on the other three sides. And so as we go through A, we go through A, we go through the battery. You'll notice you can tell we're going from the negative to the positive. So when we write our equation, we write that electromotive force there, okay? And so now as we go, so now we're going along, I'm tracing, making dots, and I pass B, and I get to a resistor. Now once I get to a resistor, I have to ask myself a question. Does anyone remember the question? I have to ask myself when I get to a resistor. It's been 2 weeks. It's definitely worth a gold star of some sort. What direction is what in, Lewis? Is it? What is it, though? Is it frittatas, steak, current? Good. So it's current. So are you going in the direction of the current? If the answer is yes, you have a negative contribution.
Wait, Professor. Oh crap! My microphone's gone.
No, I can hear you.
I know.
But you're breaking up. But if you're going with the direction of the current, right, as you trace through your circuit, then you subtract IR, right, where this is R1 here, and this is the I. If you're going against the current, then you add the term instead. Okay. So I will go over the loop law. I'll go over it again, but I want to get the whole loop in. So now we're here. And so now we go across into the circuit, and we reach another resistor. We ask the same question. You'll notice we're still going with the current. So that's I R2. And then that brings us to here. And then we have yet another resistor. Same question, same result, I R3. Now I didn't put any subscripts in the currents because we're connected in series. So the loop law tells us that once we get back to A, we can set all that equal to 0. All right? Now you'll notice using this, so again, with the loop law, I'm going to do it now with the cursor. You pick a point A, you go all the way around the circuit, and it has my microphone all. Sometimes I have to restart the microphone so that it's weird sometimes. I don't want to be screaming in your guys' computers if I can help it. So what we do is we go around the circuit. We start at A. We reach the battery, right? We notice we're going from a negative to a positive, from the negative plate to the positive plate. So then in our equation, we write, if we're going from negative to positive, this is a positive term, and it's just this value of the electromotive force. All right, remember the electromotive force is basically a different kind of voltage. It's not, I don't want to say different kind of voltage. I mean, in DC circuits, it's basically the voltage, but we're going to see cases where we have an EMF, but no voltage at all. So I do want to point out that it is different, but you have to, you got to, right now they'll look the same, but then they'll be different when we talk about AC circuits, or there'll be cases where they're different. Now, so if we went, for instance, from positive to negative, there would be a minus sign in front of the electromotive force. Okay, so that can happen, and you should be aware of that. Now, once we go to the battery, we're on the other side of the battery. We have the first term in our equation. Now we go here. Part B doesn't mean anything because we could have started there, but we didn't. But we get to this resistor, right? So now we ask, are we going with the current or against the current? So you'll notice we're going the same direction in our circuit as the current is going. So that means we have a minus term, and we have I. I'm cheating just a little bit here because I know the circuit is in series, so all the same current is through each resistor. So we have I times R1, right? And once we do that voltage drop, that brings us to this part of the circuit. We continue going until we reach our next resistor. right? And when we reach our next resistor, we have that, we ask the question again, are we going with the current or against it? Well, we're going with it, right? So we look at that, and we have a voltage drop again, and that's where we get this minus IR2. And now we get to the third resistor, and I think you can see it's the same thing. But then we get back to point A. And what the loop law tells us is that the potential around a loop is 0. Okay? So that's our basic loop law. Now this holds for any loop, and for one loop it's trivial, right? But we ended on multi-loop circuits last time, or starting multi-loop circuits, and that's what we want to talk about this time. So are there any questions on that before we move on? You'll notice in series we were able to come up with, well, I'll see if we have questions first, and I'm going to talk about equivalent resistance again, and then we'll move on. We're good?
Yes.
Okay, so the law again, this is it's often called the loop law or Kirchhoff's law, and it's basically that if you go around one loop, the voltage is 0, right? So you start here, you have all the contributions from each element of the circuit, and then you get to the same one. So if you were really going to write this in general, you would write V at A plus minus that IR1 minus IR2 minus IR3, and that's going to actually equal the voltage at A because you get back there, right? It's the loop law, Kirchhoff's law is the same thing. I can't spell Kirchhoff or Kirchhoff or say it right. But this is the same thing, but all we're looking at is that these cancel, right? And then you get this equation. And this is the loop law. So basically, the voltage around any closed circuit is 0, or any closed loop is 0. That's the law. That's it. The formal law is sum of the voltages around a loop is equal to 0. That's it. That's the law. Okay? Now, we use this equation, which is here written nicely, to come up with the equivalent resistance, right? We can treat this circuit of 3 resistors that we have right here as a equivalent circuit with just a single resistance. And we can find that the equivalent resistance in a series, with resistors in series, is simply the sum of the individual resistances, all right? Or R equiv equals R1 plus R2 plus R3, all right? And that's a consequence of our loop law. So again, I covered all this in a lot more detail in the last lecture, and I was actually playing around with the videos. They're not bad. I would suggest you look at them. I do want to give you a tip, though, for the videos. If you are having a hard time finding previous videos, they are all still up. You just have to go, instead of recent videos, there's a tab that'll say recent videos. You just put in a date range, and you start from the beginning of the semester, basically, or from March 19th. And all the videos will show up. So they're all still there, and you can find them. And they're not bad. They're not great, but they're not bad. So we covered all of this before, and now we want to start really ho-hogging here with multi-loop circuits, okay? And there's a lot to do in this section. As you can see, it's got 2 learning goals. So you'll notice in a multi-loop circuit, like the one we have here, we can actually have multiple batteries and multiple resistors. And you'll notice that we're going to talk about resistors in parallel, but you'll notice it doesn't make sense for us to talk about these particular resistances in series or parallel, right? They're just sort of attached. And sometimes the loop law is all we have. Now, when you take circuits, you'll learn a bunch of engineering tricks that make this a lot easier, but this just always works. And basically, engineering tricks, I call them tricks because if you don't have everything set up exactly like you're supposed to, they don't work. And sometimes it can seem like they should work, but then they don't. So the thing I want to ask you is, if you make a loop, how many loops do you see here? How many potential loops do you see in this circuit? I want you to think about that for a minute. Answer. So we have some 2, some say 3, 2 maybe 3, 3. Well, let's take a look. We can go A to B to D, all the way back to A again, right? That's one loop. We can also go from B to D to C, back to B, that's another loop, but this is a loop. A, all the way to C, all the way back to A, or A, D, C, B, A, the whole loop here. So there's actually 3 loops. Yeah. All right. So that's important because the number of loops give you the number of equations you can develop. And that's important because if you have, that means a circuit like this, you can have up to 3 unknowns. All right. So now what we have to look at here is that you'll notice that you have currents 1, 2, and 3. So you have these equations. You'll notice you have to start labeling the currents now. And let's look at each loop and see how they're created. So let's go through each one. So if we traverse here this left-hand loop from the point B, so that's this one, right? You'll notice we go along. We're going from a negative plate to a positive plate. So that's going to be a positive EMF. That's EMF 1, right? Or squiggle 1. Now we ask ourselves, you'll notice we assigned directions to the current. So now we have to ask ourselves, are we going in the direction of the current? We are. So we could do minus I1, R1. But now you'll notice when we go here, when we ask the same question for the first time, we are not going in the direction of the current. We're going against the current. So indeed, we need to add I3 times R3, and that's going to equal 0. Now, you'll notice for different loops, different signages emerge. And you can go around the loop any which way you want, but that's just everything to a minus sign, right? So if we traverse the right-hand loop counterclockwise, starting at point B, right? You'll notice we come, so it wants to go counterclockwise, so that's this way. You'll notice we're going with the current now, so that's minus I3, R3. We're going with the current here, minus I2 times R2, this part here. And then what's interesting is we get to C, or before we get to the battery, we start at the positive and go to the negative plate. And just as I told you before, that will give you a negative term right here. All right? So this gives us another equation. And if we apply the loop to the big one, starting here, we're starting, where does it want to start? So starting at point B, you'll notice we get to E1, and we have that here. We go from negative to positive, down minus I1, R2, we have that term here. Then as we go down across the loop, again, we're going with the current, so that's minus I2, R2, which is right here. And then again, we go from positive to negative in this battery to get back to B, so that's minus squiggle 2. So you'll notice we have 3 equations here. We could have a whole lot more than 3 unknowns, though. Right now, I see 1, 2, 6, 7, 8 unknowns. Now, if you remember the junction rule, all right, that the current coming in has to equal the current going out, the current going in at point D, right? So that's going to be I1 plus I3. That's got to equal I2, right? And this is kind of trivially the same thing up here at B, because you have out, in, out. You have, I2 coming in equals I3 plus I1. So this gives you a 4th equation. So for this particular setup, you can have up to 4 unknowns, right? So you could be expected to solve for 4 things. And without linear algebra, that can be a lot. But sometimes you can be clever and you can be clever and sort of weasel your way into easy loops instead of hard loops. I was considering solving one of the big puzzle loops where if you pick the right loop, everything becomes very easy. So are there any questions on this? I want you to look at this. Do you want to see any of it? Or point out any of it? What are you thinking? Do you see where all of these loops come from? So remember, that's the second example. Oh, hold on. Dope. What's going on? Okay, my computer went on the fritz there. Sorry. It likes the pen button likes to. So with the junction rule here, right? That's the current going in. So there's current coming I3 and I1 are coming in to point D. So that's I1 plus I3. The current in has to equal the current coming out. So the junction rule says that I out must equal I in. That's the first question, all right? And the second one, so the second example, so all we're doing here is looking at the loops. So I'll do them in different colors even. This one corresponds to this loop. All right, I'm going to change color again to green. So the second one, it's the same thing. So if you understand 1 and 3, there's nothing to not understand with 2 except that now 2 is this loop, right? And we go around this way in the loop. And then to get to the third equation, just so that we don't ruin everything, we're looking at the big loop. Okay? And we're also starting at point B and going around counterclockwise. Okay? And that's where the third equation comes from. All right? So I hope the color coding helps. I'm a big fan of color coding. Does that make sense? But Anthony had the question about being confused. I just want to make sure he's all right with it. Anthony? Good. Very good. Okay. Juia's got a great question, which is there any way to find out the direction of the current? You usually have to guess. So basically, you would just guess directions. You could even switch this around, and you'll know if you're correct whether you get a negative sign. So it's when you're working on this on yourself, it's kind of arbitrary. And that could very much change the junction equation for sure, right? It could change this equation. But what the reality is that you'll just be off by a minus sign. So you expect all your currents to be positive, and then if you get one as negative, you made a mistake in the direction. You have to change it. Okay? All right. So, make sense? All right, I'm gonna go. Right, so the last part here is these, you just pick any which way you want to go, but when you're looking at a junction, right? And I'm going to clear what's written because we have that. You can go back and look at it at a later point. If you look at a junction, it doesn't make sense. For example, there are some limitations. You can't pick all of the current going out of the junction. This would clearly be wrong, right? So you basically pick your directions. You make sure you have at least one current going in and one current going out, and then the other one is up to you. So for instance, if you're looking at this problem and you said, okay, this one's coming in, I1 comes in, and I2 goes out, 3 can really go down or up. It's fine, right? You just want to be consistent. So that would be, you could have that. But again, if you pick the wrong direction, all that happens is you're off by a minus sign. But there's no way, you just sort of get used to, as you solve more circuit problems, you get used to picking the right direction. But every once in a while, everyone picks the wrong direction. So you just have to sort of make the choice, do the analysis, and then see if you got it right. Like I said, though, you'd only be off by a minus sign. So that's all that would happen if you pick the wrong direction. But the directions are arbitrary to the point of that you have to have at least at a junction, you have to have current both entering and leaving the junction. That's required. Okay? All right. Let us go through here, and we're going to look at resistors in parallel. Okay? So if we look at resistors in parallel, much like we saw with capacitors in parallel, you'll notice we have this nice we only have one battery. This makes the currents easy to figure out, right? They'll all just sort of split down each of these branches, down here, down here, and down here. And now we know that even though we have different currents going across each resistor, each one of these points connects to the positive and negative end of the battery. So the potential difference across each of them will be the same. So when we look here, and we sort of start with the, we know that I1 will be equal to V over R1. I2 will be equal to V over R2. These are semicolons I have in between them. I3 equals V over R3, right? The voltage stays the same. So in fact, we know that the current I will split into I1, I2, and I3. And we know that if we add all of those currents together, we have to get the total current. So I will be equal to I1 plus I2 plus I3. Okay? And that comes from our junction rule. But now we can plug in each of these, right? We can plug in each of these terms into our equation. All right? And when you factor out, so you'll notice they have it here, but since all the V's will be the same, you can factor out the V's out here, and you'll notice you have a nice term and you'll notice that if I equals V over R equiv, which we have here, we can see that in parallel, 1 over R equiv is equal to 1 over R1, right? Plus 1 over R2 plus 1 over R3. So you can see that in parallel, 1 over the equivalent resistance is equal to the sum of the 1 over Rj's. But you have to be careful because you have all these in the denominator. So you have to, recall your ability to add fractions, and you'll have to do that. So finding common denominators will be fun times for you. Now, what we can see, and I think we have this in the next one, this is what I wanted to do, is we can compare our rules for resistors and our rules for capacitors. And I want you to review that really quick and notice the difference between them, right? They're similar but different. So take a look and sort of let it marinate. Sorry. My head hurts. Well, sort of. Capacitors allow charge to be stored, not necessarily flow. So capacitors in some ways look like batteries, but capacitors work on the principles of electrostatics completely, and batteries work on chemical properties, namely electrolysis. So you'll notice, what I want you to see is you'll notice that the series rule looks like the parallel rule for capacitance, right? And vice versa. The rules look the same, but you'll notice they're different. The one for parallel, capacitors in parallel just add, whereas in series it's 1 over the equivalent capacitance. In parallel, it's 1 over the equivalent resistance, whereas in series the resistors add. Okay? Now, this brings us to our fun example time. We are going to be doing lots and lots of examples. So if you were wondering, is he going to do examples of this stuff? The answer is yes. We will be doing examples. We're going to start out small, and we are going to what? Oh yeah, Lewis.
If the resistor series is similar to the capacitor's parallel, would it be the same for the resistor's parallel to be similar to the capacitor series?
Well, yeah, you can see the slide, right? They're both up here. So you have it in series. So this is capacitors in series. I'm highlighting it, and that's resistors in parallel, and resistors in series here, capacitors in parallel. So it's the form of the laws are the same, but of course capacitance and resistance are different things. They're not the same physical phenomenon. But you'll notice that because the adding them in parallel and series is based on voltages being the same through each parallel branch and currents being the same through all series branches. In lab, what I ask you to do is to develop these formulas for resistance, but to do it experimentally and get a real sense for how it goes as you add a resistor.
So what do these relations allow?
What the what?
What do these relations allow? Like,
so these allow you to reduce complicated circuits, like we saw before with multiple resistors, into equivalent resistors. So you can represent this 3-resistor circuit as an equivalent 1-resistor circuit. All right. And so, for instance, if you have these 4 currents, you can reduce this. And like I said, we're going to see a lot of examples, and we're going to do some. But for instance, if you need to solve for all these currents, you can't. There's too many currents to solve for here. But if you make an equivalent circuit, right? Because you know each of the resistors, for instance, you can then solve for the current, and now you have, and that gives you I. And now you can sort of break each part down and solve for the different parts of it, or use your loop law to solve for different parts of the circuit.
Okay, got it. And the EMF is also charge flow, right? Also.
The EMF is a voltage; it's potential difference.
Okay, got it. Thank you.
All right. So let's look at this checkpoint. All right. So we've got a battery with potential V across it. Is connected in combination to a combination of 2 identical resistors that has a current through it. So what are the potential difference across the current through either resistor if the resistors are A in series and B in parallel? So you want to try and draw that first, right? Draw the series circuit, draw the parallel circuit, and then you should be able to get each of those pretty easily, especially since the resistance is the same. Oh, good. I have two examples. So yeah, we're going to be doing 3 examples. So I wanted to count them. All right. So I'm going to draw the series circuit up here in green and parallel circuit in another color, probably yellow. So each one has a battery. It's a crappy battery. All right, I'm going to use my magic eraser powers to go. God, I hate this. This is not working for me. There's one. There's two. All right, it's going to be good enough. So let's draw the series circuit. So we'll draw one resistor and a second resistor. All right, so that's the series circuit. And then in parallel, I wish I could say my drawings were better in class, but that might be a lie. All right, and that's the parallel. And I want you to keep in mind our definitions hold. So our R1 and R2, or they're not R1 and R2, they all have the same resistance value, right? So when we look at them, when we look at them here, in parallel, they're both, this resistor ends at the positive terminal of the battery and ends at the negative terminal. And the second resistor R also ends at the positive terminal of the battery and at the negative terminal of the battery. Okay? So that they both have to end at the same place to be in parallel. And in series, you'll notice that the current stays and doesn't branch off anywhere. So it goes through. So with that, so what I'm hoping first, before you answer the questions, were you able to draw these two circuits? If you have questions about drawing those two circuits, let me know, and let me know what you get for your answers for part A and B. And remember, so A, well, let's think about what they're asking here. We want to know, so if we have a voltage V, right? We have a voltage V for each one. So it wants to know the voltage across each resistor. All right, so V does equal IR, but we want the voltage, we want the potential difference across the current. Yeah. So basically what you have to look at is if you take a probe, right, and we talked about this, and you measure the voltage, here you'll get V. So the voltage across both resistors in series, right, we're doing A first. In B, it'll be V across each. So here, you'll have the same current through each resistor, right? But if each resistance is the same, you'll have V over 2, V over 2. You'll have a little, well, not really a voltage divider, but the voltage will be divided across each resistor evenly. All right, because again, if you have the voltage drop across here, it's got to be the same thing as the voltage drop across all of the resistors. Now, if they have the same value, they'll each contribute V over 2 and V over 2, because when you add them, V over 2 plus V over 2, it's got to equal V. Or another way to look at this is V, right? If you don't believe me, V minus V over 2 minus V over 2. I'm just using the loop going around, right? I'm going to claim that equals 0. Right? V minus V over 2 minus V over 2 is V minus V. V minus V is equal to 0. All right? Now, in parallel, we know that the voltage will be the same across each resistor, but the current through each resistor will be I over 2 here, because again, the total current You have to have the current will split at these two branches, but then when they recombine, they have to equal the total current here. Both the resistors are the same using Ohm's law. You'll see that you indeed get half the current. Okay? So see if that makes sense. Think about that for a couple minutes. Okay. So let's take a look at. I want to do this. I want to do this on the whiteboard because I want to make the circuits bigger. So this might be a little traumatic. So if you need to, take a screenshot of the checkpoint or whatever you need. But we'll come back to this. So I want to make bigger circuits because I really want this idea to get slammed home too. So we're going to draw our two. So we're going to draw our two circuits. All right. So we have potential difference or squiggle. We have R and we have R. And we'll have a current I. All right, going around. So for part A here, I is going to be the same, right? So we want to know the voltage. We want to know we want to know the voltage and current basically through each resistor. Now in series, the current is trivial, right? The current is I, and the current is I. So I is I for R, for each R. So just one thing at a time. Does this make sense? Ready to go on from here? Okay, good. So if that's the case, then the voltage as round, right? I mean, we can do it numerically. We could start here. We have a voltage minus IR minus IR, right? That's going to equal 0. So if we want the voltage across each one, we can see that V minus 2IR equals 0. V equals 2IR. And if we just solve for IR, that's the math. However, I expect you all to see that argument from the loop law. But I want you to notice that you can develop intuition about the circuit, right? Things to notice. The resistances are the same, okay? And as you become familiar with that, you have a voltage rise, a voltage here available to you, and you have two voltage drops. If the resistances are in series and are the same, then each one must contribute an equal voltage drop, and therefore your voltage across each resistor is V over 2. But you can certainly use the loop law to derive the same result, right? The voltage across the resistor is IR is equal to V over 2. Does that make sense? We're good on the series one? We're good on the series one? Okay, good. So let's move on to the resistors in parallel. All right, so we're getting rid of that circuit. And do keep in mind all this stuff will be on the recording too. So, all right, so we got to draw another circuit again. That's fine. All right. So we have again V, R, and R. But now I want to be a little creative here. We have our current I, right? We have a current I here. And we're going to do our other currents. Call this I2 or I1 and I2. Okay? So that's what's going on with the circuit, basically. All right? And this is wired in parallel. And again, it's wired in parallel because at the junction, each resistor ends at the same place, right? They both connect to the positive and negative end of the battery and to each other, right? So this resistor goes to the positive terminal. This resistor goes to the positive terminal. On this side of the resistor, it goes to the negative terminal. Same thing with this resistor. It goes right to the negative terminal. That makes them in parallel. So when we're looking at this, we can see if we make loops, it should be pretty easy to see, but again, each of the resistors are the same. So what I want to argue here is that I know that in parallel, right? In parallel, the voltage is the same, and equals V for R, right? But we can see if we have the same voltage, in each branch and the same resistance, and there's two resistors, well, logic tells us that the current has to split evenly among each branch. It shouldn't be able to tell the difference between each resistor. And so therefore the current is equal to I over 2 for R, for each R really, okay? Now if you want to see it in terms of the loop law, you can do that. You can start here with, you can start at a point, go around, and you get V minus I1R equals 0. And you also get V minus I2R equals 0. This implies, I'm going to let you do the math, that I1 equals I2. And then using the junction rule, I equals 2I1, right? You can get that I1 equals I over 2. So either way, you want to do it mathematically or argue your way through it. Each way, you get the same thing. Okay? Good? All right. Back to the PowerPoint. Again, now that I have 21 of you in here, I want to remind you all that the exam is tomorrow. So I'll talk a bit more about that probably during the break. And if you want to stick around after class and have questions, we can talk about it. Yeah, you've had 2 weeks to study. All right. So we want to go right to our next example. All right. So let's read this problem and let's see if you can work on it, and we'll sort of work on it interactively, and I will go over it. I'll give you about I'll give you 5 minutes or so, 5 or 6 minutes or 10 minutes to work on this. Well, actually, just 5, and then we'll see what questions come up, and then we'll go over it. I think after break. So I think we might even extend break. So 5 minutes is official for you to work on it, and I'll be here, and then we'll take our 15-minute break, and you can still work on it if you want, and if you'd like, and then when we come back from break, we'll go over it. Okay. So let's read it now. That'll be part of our 5 minutes. You're already working on it. So we have a multi-loop circuit here, right? And it contains one ideal battery. So thank goodness, just one battery, and 4 resistances with the following values. So we're given all of our information in a table. And if you're working on a homework problem, I would say making something like this to keep track of all your information is probably the right call. And we want to know what is the current through the battery, and we want to know very specifically what is I2 through R2. Okay? So I'll let you have some fun working on that. And my hint to you is ask yourself, and my first question for you to consider before before I send you off working, because now you only have 3 minutes until we go on break, is R2 in series or parallel with R1? Series. Good. That is absolutely incorrect. In order to be in series, you need to not pass any junctions in a loop. Right? You're here, you're in a junction. The current through R2 is not equal to the current in R1. Can't be parallel either, because in order to be parallel, they both have to start and stop at the same place, and they do not. R2 does not connect to the terminal of the battery, where R1 does. It is neither. Good. So you have to think carefully about how you make your equivalent circuit. All right, now I'll let you work. Mm-hmm. Well, generally, it's easy to tell in a single battery circuit because we always have the current go in this direction. Choices become difficult when there's multiple batteries, but then the current, if we start the current going this way, we're going into the junction, and we can assume that the other currents would have to go out of the junction, right? All right, we are officially on break, so I've got to take care of some stuff in my kitchen, but I'll be back. We'll start up again at 7, but I'll probably be back at 5 till. So I'm gonna go away, and I'll see you all in 10 minutes. I've returned. A little later than intended, but I've returned. All right. Okay. So, oh boy. So, all right. So let's go over this example. So does anyone want to give it a shot? What did they think? What do they think the currents are? Well, while you're writing your answers, you're still figuring it out. Let's kind of go over it. So I'm going to clear here. Now, even though R1 and R2 aren't in series or parallel, we could redraw the circuit if we wanted to, which I'm going to do up here because it's not an equivalent circuit. So I want to do the pencil. We could draw it like this. And we notice that R2 and R3 are in parallel, right? They both begin and end at the same electrical point here. These both connect to R4, and on the other end, they both connect to R1. So we can look at how we would write this is we would say if they're in parallel, we'd say that R, oh, I don't want that to be that big. Come on. Let me delete that. So we can look at this and we can go, we would write this like this, 1 over R 2, 3, right? Because that's the equivalent resistance of 2 and 3. We can combine them. And we can say that's going to be equal to 1 over R2 plus 1 over R3. Right, and that's going to be equal to 1 over 30 plus 1 over 20. Right? So you can figure that one out for yourself, but then once you figure it out, you have to flip it. So I would do the arithmetic first and then flip, because you don't want to make the mistake and flip it and think it's 30 plus 20. That's not true. So let's see, 1 over 30. I'm a little tired, so I want to tell you to just do it on your calculator. Will be equal to 50, or not, I'm sorry, 30 plus 20 over 50 times 20, right? No, I'm sorry. See, I'm already losing it a little here, everybody. Times 20. Right? So that will be 50 over 600. But then, and now we can flip it, right? So R equiv, or R23 is going to equal, and I think someone already had it, that's going to be 60 divided by 5, basically, which is 12, right? So R23, we'll add it here, R23 equals 12 ohms. Okay? So not 1/12. Remember, 1 over R23, they're in parallel. It's 1 over R23 is 1 over 30 plus 1 over 20. So 1 over R23 is going to be 50 over 600. After you do the addition, then you flip it. Okay? Make sense? So that's where you get this. And now what you can do is you can draw an equivalent circuit that makes life a little easier. Right. Good, Mustafa. Now we do a new circuit, and we have here, we still have R1, but now we have R23 And we have what? R4. Okay, so now we can make an equivalent circuit because these will all be in series now, right? So that one's easy. So R1, 2, 3, 4 will be equal to R1 plus R2, R2, 3 plus R4, and that's going to be equal to 20 plus 8 plus 12, so that's going to equal 40 ohms. All right, and now, this is even more exciting, we can make this into one equivalent circuit with one resistor. And we know the EMF, right? We have that's equal to 12 volts here. And we now know R1, 2, 3, 4. And so this lets us just use Ohm's law, right? Which is E equals IR. And we can solve for I equals epsilon naught over R. And that will be equal to 12 over 12 volts over 40. And that's equal to, I brought my iPad so I have a calculator because my powers to do this are definitely, but I think Julie's right. 0.3, very good. So I is equal to 0.3 amps, right? We want to be good with our units. And that's how you get the current in the battery. So take a look at it, see if you have any questions, see if anything sticks out or looks bad. The order of R1, R2, and R4. What do you mean the order, Lewis? I'm not sure I know what you mean. So how we got from this one circuit to the other one, or? Oh, well, so once we realize that these two are in parallel, right? We can solve for R23, which was the first bit of business we did up here, right? And then we can make an equivalent circuit where we have R1 and R4 unchanged, but now we can say that R23, we can replace that with this parallel combination here. And that gives us R23. But now we just have R1 is in series with R23 and R4. So it's not R2 or R3, it's R23. It's a new resistance, right? That we get from combining R2 and R3 in parallel. And then once we do that, we can say that the equivalent resistance, or R1, 2, 3, 4, right, for all of them, will just be equal to R1 right there, plus R23, plus R4. All right, because that's how we add resistances in series. And then we can make the equivalent circuit with just the battery R1, 2, 3, 4, and from there we can get the current. Does that make sense? Good, good, good. All right. Now we have to do part B. So I'm going to leave this up just for a little bit, and then, or for about 10 seconds, and then I'm going to delete it all with our keeping in mind some of the things we know. So I'll write those down because I don't want them to disappear. So give me just 1 second. Actually, that'll give the perfect amount of time. R23 equals 12 ohms. And I equals 0.3 amps. And And then we know that R1234 equals 40 ohms. All right. So having seen all this, well, actually, I might not be able to delete all. Well, yeah, I'll delete it all. So things we want to start with, keep in mind from the previous part before we start. So I'm going to redraw some of it. So in order to find the current through the second resistance, right, now I want to keep in mind the stuff from part A, because I can't do part B without part A. So interesting things we learned in part A is that I is equal to 0.3 amps. Right? We learned that R23 is equal to 12 ohms. We learned that R1234 is equal to 40 ohms. And we want to start off again. We want to start with our single circuit, our equivalent circuit, right, with just one resistance. We'll call that R1234. We'll draw our little squiggle, our little epsilon squiggle. But now what we want to do is we want to be able to break the circuit apart. So now we have to go back. We want to decompose again, right? Because we can't just start from the circuit and get it. And in fact, we need to go all the way back to our equivalent circuit to break it down, even if we wanted to. But we want to keep everything in mind here, because we did find that the current through the battery is 0.3 amps. So what we know is that breaking it back down, right? We can look here, and we know that the current that we found in part A is the current. So this is R1, R23, and R4. We know the current is the same through all of these resistances, right? So if we know the current is 0.3 amps that we use from part A, and we have all the R values, we can find I1, I23, and I4. These are all now can be known numbers, all right, because we have the voltage through each of these three resistors, right? So we know R, and we know the current. So we can just use Ohm's law to get the voltage drop. We can calculate. Well, we know. Sorry, I messed that up. Blah. We know that the I is the same from part A, so that the this headache is getting the better of me. We can know V, 2, 3. We can figure out all these voltages. All right. Now we won't need to figure them all out, but if we come across one where we need one, these are all known now. Okay. And you have R, you have I for each resistor, right? You have I for each one, and you have the R values. You can multiply them in. Now, we know we want I2 through R2, so we can just concentrate on this part here. So we know that the voltage, V23, is going to be equal to I times R23, right? And that will be equal to 0.3 times 12. So 0.3 times 12 is going to be 30% of 12 is going to be 3.6. Did I do that right? I think I did that right. I did that right. Did I do that right? Yes, 3.6. Now I have to use the I. Now this is sad. This is a sad state of affairs. Yes, I did do that right. Okay. So V23 is equal to 3.6 volts. Fun. All right. And now we can break it down to the original circuit again, right? So we know the voltage is the same for V23 and 23 will apply to both of these resistors, right? Because they're in parallel. And then all we have to do is remember that if V equals IR, V23 will equal I2 R2, right? And so all we have to do is solve for I2 equals V23 over R2. That's going to equal 3.6 divided by R2 is 20. So that's going to be equal to 0.18 amps, I believe. Yeah. Anyone else get the same thing? Good. Does anyone have any questions, though? The loop rule is always a valid way to do this. I just wanted us to practice looking at series in parallel and applying the rules. But yes, the loop rule is always valid, and in some cases might be easier. But you'd have to solve, if I were doing the loop rule, with the loop rule, you have to solve everything simultaneously, though. That could be a pain in the butt. So if you're going to do the loop rule correctly, you don't know, you have three unknown currents. You have unknown currents and unknown voltages. You have to set up a lot of equations to do that. Okay? So, all right. Now we have another example. So I hope we're getting exampled out, full of examples. All right. So I wanted to pick a homework problem that I thought might be fun. And it's very similar. So you'll notice the current in resistance 6 is 1.4 amps. And the resistances are R1 equals R2 equals R3 equals 2 ohms, R4 equals 16 ohms, R5 equals 8 ohms, and R6 equals 8 ohms. So we want to know what is the EMF of the ideal battery. So we want to solve for this EMF. Okay? So I'd say hop to it. I want to give you a couple minutes to sort of try and figure this one out too. And see what kind of questions pop up. Think about the last one we did. It's pretty much the same problem. It's just that we've added another branch to it. So there's a little more work and a little more algebra. I think if I wanted to be really evil, I would put another battery like right here. But we didn't do that. So I would recommend for you to draw the circuits, each one, which can be a little tedious, but you'll always be structured and go the right way. I think I might take it a little short, but we just have to look at, you'll notice that if you look at the circuit, right, R1, R2, R2, R4, we have to start from the end and sort of collapse our way back. All right, so starting with R5 and R6 are the first ones we can say are in series, yeah? And we have the current I6. So we know that I6 is actually also equal to the current across R5. So if we look here, we can say, we can look at step 1. Which is to combine R5 and R6, right? Because that'll just be equal to R5 plus R6. And then we can look at that and we can say, okay, we know the current through each of these. And so we also know things we know. We know all the R's. These are given in the problem, right? And we know I6. And basically, we know that I6 is equal to I5 because they're in series. So, so we know that, and that will help us get V5 and V6. All right. So if you look here, you can just, V5 equals I5 times R5. So those are just numbers, right? And V6 is the same. I'll write that as 6 actually, because that's what's given in the problem. So we can do that and get those numbers. So this is our table of known stuff. Now let's give it some numbers so we're not, because it'll get out of hand pretty quickly. I'm just going to leave our knowns up here, but I'm going to make another table. I'm going to delete some of the stuff here. All right. It's just kind of an involved problem. All right, so we know R56 is going to be 8 plus 4. So hold on. R56 is going to be equal to it's going to be equal to 8 plus 4 is 12. Yes, that's the next step. I haven't gotten there yet, but that will be the next step. Or we did that we did that. What we're going to find is, I'll show you. So I'm finding I'm probably going to need to draw the circuit, but I'll just draw the part I'm concentrating on. So we know that. R56 is 12. So V5 is going to equal I'm not sure we need all these voltages, but we might. V5. Well, let's see. Right now, I just want to get the equivalent resistance. No, because I'm going to need the current for the whole thing. So I am going to need these. So V56 is going to be or V56 rather is going to be equal to I6 times R56, right? And that's going to be equal to I is 1.4 amps times 12. 1.4 times 12 is, someone help me with the calculator here. I can't keep doing it. Good, 16.8. So that's going to be equal to 16.8 volts. Okay. So now what we want to do is, good. We want to notice that if I look at, I'm going to redraw the equivalent part of the terminals I've drawn here. What we can see is that V4 is in parallel with, or R4 is in parallel with R56, right? And so what we can do there is we can look at, we will note that because they're in parallel, the V's are the same, right? So we know that V4 equals V56, right? Because those are in parallel. And with those being in parallel, we want to find, I'm going to put a box around this set of calculations. I'm going to call this 1. I'm going to change colors. So 2, our second box here, now we're going to want to look at R4 or R456. Okay? So let me break it into little parts. And so now we note that that R456, right? It's in parallel, so we know that that to the -1 power is going to be equal to 1 over R4 plus 1 over R56. All right, so that's going to be 1 over R456 equals 1 over R4, that's going to be 1 over 16, plus 1 over, what did we say R56 was, 12? All right, so divided by 12 plus 1 divided by 16, and then 1. Oh, wait a minute. I get 6.85. So, all right. So that's going to make this equal to 6.85 ohms. All right. So now I'm going to I have these taken into account, and now I can move my terminals, right, back for blue. And if I draw the circuit in blue up here, it might be hard to see, but between the new terminals, now I have R2, my system, and then back there, so this is going to be 456, right? And this is going to be R2. And these are in series. So we have that, but we want to be sure we calculate everything we need before we move on. So once we got our here, we had our voltage across R4. So we know the voltage across R4 and R6. It's going to be, so we'll have the voltage, so we can find here. So for 3, before we get started, we have one more thing. We'll have that V V12 V4 456 is going to equal I 456 times R 456, right? So we can figure out the current here. So we have the voltage, and the voltage will be the same from 1, 2 to the equivalent voltage, right? So from there, we can say that V56 is equal, this is also equal to V456, because they're in parallel, right? So it's a V4, V456, we make them equivalent. And now we can get I456. So let us look at that. And we can look there. I'm doing this because I have a feeling what we're going to need to do is get an idea of what the total current is. So if we look at the equivalent circuit, right, of here, we'll know that the current going through 456 has to be equal to the current going through R2, and then we'll have the current sort of for this part of the circuit. And once we get, the goal is that once we get all the way back, we'll have the current for the entire circuit. Once we have the current for the entire circuit, we'll have, and the equivalent resistance, it will be easy to solve for our epsilon naught. Okay? As you can see, keeping track of it is a little difficult. So, you know, we'll keep going. So let's see here. So I 456 is equal to it's going to be equal to V456, which we know, right, over R456, which we just calculated. All right. So now we can look at, now that we know everything about 6, we can look at our part here. And so we know that I456, because they're in series, has to equal I2. All right? And we know that R2, 4, 5, 6 has to equal R2 plus R4, 5, 6. These are known, so we will say, we'll give a number here. So V456 is 16.8 volts over what's R456. What did we get for the? Did we get a current? No, we did not. Right. So I456 is going to be 18.6. What's R456? What did we agree on there? 6.8. I'm going to just trust you there. Too many numbers. 6.85. Right. Oh, we got no. That's the 6.85. That's what we got there. Sorry. No, I got you. So we want to do 16.8 divided by 6.85. And we get the current. .85 amps. And so that's good. We have that. And getting the resistance should be pretty easy here. So we have our 6.85 again, right? And we're going to add that to R2, which is given in the problem, which is 2. And that we're going to have as 8.85, right? So equals 8.8. Oh. It's a little sloppy here, but right. So then we get 8.85. And now we just do the same thing again, and we're almost done. We're almost home, but now we want to move our leads back to here, where we'll see that will be that will lead to a parallel combination of I'll just draw the resistor in here. So we'll have R3 will be in parallel with 2, 4, 5, 6. Okay. And now let's change to a different color. Let's go to yellow to do that. So we'll call this box 4. I'm labeling these 1, 2, 3, and 4 so you could follow them along potentially, because as you can see, if we didn't change colors, this would get pretty bad pretty quick. So for 4, we want to look there where we have our equiv, or R2, 3, 4, 5, 6 is going to equal, and that's going to be to the -1 power. Yes, they are. 1, 2, 3, and 4 related to each resistance. It's going to be 1 over R2 or R3 plus 1 over R2, 4, 5, 6. And so that will be equal to, so we'll have 1 over R equals, I'm just going to do the shorthand, 1 over, I'm going to say 2 through 6. 1 over R is it's going to be equal to, so what's 1 over, that's 2 again, right? R3 is equal to 2. And then we have 1 over plus 1 over 8.85. Okay. And that will give us 1.63. I'm going to trust you on 1.63. R2 through 6 is going to equal 1.63 ohms. All right. And then what do we need? What do we need? We want to be able to get the current of this sucker, right? So we knew the voltage from the previous one because we have, where did we calculate that in 3? Going back here. So we knew we have R23, right? We have the current of I23, so we can definitely calculate the voltage. So I'll do a calculation here. V 2, 4, 5, 6 is going to be equal to that I times R, right? And we found I, so that's going to be, because those were in series, right? So I4, 5, 6 would be equal to I2, right? So then we'd have, so we have I4, 5, 6. That's going to be 2.85 times 8.85. What do we get for the voltage there? Oh, it's 2.45? Okay. Well, at least you know where mistakes are going to come from. They're going to come from messing up numbers like this. And writing down something wrong is inevitable. Are you sure it wasn't 2.85? I thought someone got it's 16.8 divided by 6.85. That's 2.45? Okay. I will trust you all. Let me make sure I didn't mess it up somewhere else. 2.45. There we go. So if we have 2.45 multiplied by 2.85, so then we'd have V2456 is equal to, I don't know, what's it equal to? $21.68. All right. So fun times. So now that we have that, we know we can also figure out the voltage, which will bring us back here because we want this whole thing. But we can also figure out the voltage on R2, right? Because we know that the voltage on 2 will be equal to I2, which we already know because we can use them interchangeably, times times R2, so that's going to be 2, right? I2 times 2. And we get here that voltage is going to be, so we get the voltage for R4, 5, 6. We need the voltage for R2 as well, because those will be different. And that's going to be equal to 3.26. All right, thank you. 3.26 volts. Okay. So hopefully no one's lost. It's a very real possibility. So now we're back to looking at wanting to combine. Again, we're looking at getting R3 in there, right? So we know we have our equivalent now, R23. We know that R3 it has the same voltage as R2345. So to get V2, right? To get V2345, or to get V, what is, so to get, so we have V2456, right? I don't think we needed V2. I think that was just extraneous. We know V2456 is equal to V3, right? Because of the they're in parallel. All right, so I'm actually gonna, we might need this, but we might not. So we know that V3 equals V2456, which we did calculate over here. And we know that that's equal to 21.68. And so we know that that voltage will be the same for both resistances and their equivalents. And so all we need, so we calculated the equivalence, right? So now all we need to get I to 4, 5, 6 is all we need to do there is to multiply our voltage, or this would be I2 through 6, sorry. Okay, so we know that's there, and we want the total I through. So yeah, so this is, so I2, hold on. I2 through 6 is going to equal I2 through 6 is going to equal our voltage, right, over our R2 through 6. And so this will be equal to the voltage that we have. It's the same, so we can do voltage which voltage are we doing? Right, 2456. Because 2456 will be equal to, have that same voltage, and that will be 21.68. That's going to be divided by our equivalent resistance, which is 1.63. So what do we get there for our current? Anybody? Use those fancy calculators. 13.3. Okay, good. So now we're getting to high currents here. So that's going to equal, so I 2 through 6 is going to equal 13.3 amps. And now finally, we can move our goalposts right here to get to the full circuit. And now we're just going to have R1 in series with the other stuff, right? And so we can look at that as the equivalent resistance. We'll make this into box 5. So we already know the current. We can use this current. So that's the current through the whole circuit. That's pretty cool. That's I. All we need is R equiv is going to be equal to R1 plus R2 through 6. So that's going to be 2 ohms plus 1.63. So that's going to be 3.63. And finally, we can say that our EMF through the circuit, through the ideal battery, that is going to equal our 13.3 amps, I2 through 6, or I1. I'm going to write it here because this is equal to I1, because they're in series, times R equiv. That's 1 through 6, right? And we have both those numbers, so we can multiply 13.3 times 3.63, and that should give us our final answer, which is, someone drum roll for me. 48.28. All right. And we finally, after all that work, have it done. So I'm hoping you see how to deconstruct one of these problems. And it takes a while. It's a lot of little algebra, but it's a lot of really easy steps, right? And so I want you to notice, I'm not going to go through everything, but I want to summarize how to follow this problem when you're looking back at it. All right, so I tried to make a table of everything we knew, but that got out of hand pretty quick. And so what I did was I started with the easy stuff, right? I just did this part in my head, and I wrote a circuit down here, R5, 6, and R4, just focusing on, I just did this because I knew how to do it because those were in series. And then I added them together, R5, 6. It looked easy. And then when we got to 2, I made a little dot here. And so this dot corresponds to this circuit. And then we changed colors, and we had to do the analysis for that circuit, and so forth on to 3, 4, and 5, all the while solving for various currents and voltages so that we could reduce the circuit and eventually solve the equivalent circuit, which just has the current, the EMF, and the equivalent resistance, and then we could get our EMF. All right, so if you want to follow this, follow the circuit decomp. I would suggest you redo this and do the circuit decomp and then match it to each of the equations in the analysis. All right, hopefully you can read that. I'm getting pretty tired. You guys have a test tomorrow, so I'm not going to push it. So you might want to come back to this when you're more focused on not having a test tomorrow. And what we're going to do is we're going to do RC circuits and then move on to magnetic fields on Thursday. Okay? So I'll stick around. I'm going to stop recording the lecture. So I'm going to stop that now so that it processes.